Okay, so a while ago, this guy Maxwell Planck was basically hired to try and improve the incandescent light bulb. The incandescent light bulb works by heating up a filament, so it's kind of connected to this thing in physics we call black body radiation. The issue was the old theory, sort of classical thermodynamics, predicted one outcome, but when they did experiments, they got a completely different outcome. So this guy named Planck, he looked at the theory to try and come up with a theory that would match what experiments were doing, and he got this relatively simple looking equation that the energy of light is equal to a constant multiplied by frequency. After the fact, we now call the constant Planck's constant, and it's got a value of 6.626 times 10 to the negative 4. It's got funny units of joules times seconds, and then we're multiplying that by frequency. Frequency is the frequency of the light. Really what Planck's equation did is buried in there, what he's saying is that, let's say we pick a frequency of light or a particular color, let's say orange light. Orange light delivers the energy that it delivers in multiples of whatever h times f is. If we could shoot one bullet of orange light, it would deliver energy of whatever h times the frequency of the orange light is. If we shoot two bullets, then we get twice as much energy. Three bullets, three times as much energy. A million bullets, a million times as much energy. We're not allowed to have any other energy for that orange light other than multiples of whatever h times f multiplies out to be. So really what that means is that the energy of the light is quantized, delivered in chunks, and really what that means is that light is behaving as a particle. We're going to come back to that in the lab. Now a weird thing is we don't usually talk about light in terms of its frequency. We usually talk about light in terms of its wavelength. But if we go back to grade 11 physics, we have that universal wave equation, V is equal to F times lambda. If we're talking about light, then the V is the speed of light, so we could say C for speed equals F times lambda. Or if we rearrange that and bring the lambda to the other side, F equals C over lambda. Planck said E was equal to H times F, and then we now know that F is the same as C over lambda. So wherever I see F, I can write down C over lambda, or I get kind of a new version of Planck's equation, E equals hc over lambda. The lambda's on the denominator, so that's an inverse relationship. The bigger the wavelength, the lower the energy. In a way, you kind of already knew that. Red light has a shorter wavelength that has more energy. Infrared isn't visible, it's just outside of red on the shorter side. An even shorter wavelength means even more energy. That's the one that gives us sunburns. So you always protect from UV when you're outside because the energy of the UV light is high enough that it could give you a sunburn. For fun, if we plugged in some numbers, each color has a range, but let's say we go with orange, and we say that the wavelength of orange light is 600 nanometers. We can figure out the energy of each particle or each photon of orange light just by cranking out Planck's equation, 6.626 times 10 to the negative 34. That's the constant. It's got those funny units of joules times seconds. C is the speed of light. It's 3 times 10 to the 8 meters per second, all divided by our wavelength of 600. If we put that in meters, is 6 times 10 to the negative 7 in meters. If you look at the units wise, meters cancels with meters, second cancels with seconds. We're going to get a number in straight up joules, which is good because it's an energy. And within rounding, I've got 3.31 times 10 to the negative 19 in joules. So orange light with a wavelength of 600 nanometers can only deliver energy in multiples of that 3.31 number. It's kind of like saying if we got rid of electronic money in Canada, you could only have currency values that are multiples of 5 cents, since 5 cents is our smallest piece of, literally piece of money. Orange light can only deliver energy as multiples of that smallest number. Orange light can't deliver 4 times 10 to the negative 19 joules of energy. It can deliver 3.31, or if 2 photons of energy were involved, then we double it and we get 6.62. If 3 were involved, we triple it. but each little bullet of orange light would deliver 3.31 times 10 to the negative 19 joules of energy. If we change it up, if we did 400 nanometers, nanometers, that is, I don't even remember the color, that's a shorter wavelength, Roy G. Biv, so we're probably into the blues. If we calculated the wavelength of that, we would do the exact same math. 6.626 times 10 to the negative 34. The speed of light is 3 times 10 to the 8. The wavelength in meters is 4 times 10 to the negative 7. Cranking that out, basically what we said was E is equal to hc over lambda. Cranking that out, since it's a shorter wavelength compared to 600, we should be getting a larger energy. As wavelength goes down, energy goes up. Rounding it off, it's almost 5, 4.97 times 10 to the negative 19 joules. That's kind of how we use Planck's equation. The mechanics of it are E equals h times F, or we could replace it with hc over lambda. And the cool sort of theory behind it is the fact that the energy is being delivered in these bundles implies that the light must be particles, which is something we'll have to talk about a little bit more as we work through quantum.